This question asks you to identify true statements about the ShrunkCovariance method in Sklearn, a Python library for machine learning. We'll explore how ShrunkCovariance handles covariance matrix estimation, especially in situations with lots of variables and noisy data. I found that this statement is true. ShrunkCovariance cleverly ensures the resulting covariance matrix is always positive semi-definite. This is a big deal because it prevents mathematical problems that can arise with other methods, especially when dealing with noisy data or many variables. A positive semi-definite matrix is essential for many statistical calculations. Yep, this one's also correct. The power of ShrunkCovariance really shines when you have many more variables than data points. In these high-dimensional scenarios, standard methods often create unstable or singular, non-invertible, covariance matrices, causing problems in analyses. ShrunkCovariance neatly avoids these pitfalls. Absolutely. The ShrunkAGE parameter is like a dial. It lets you adjust the mix between your raw data's covariance, sample covariance, and a more stable, theoretical version, the Ledwall-Wolff target. At 0, you use only your data's covariance. At 1, you entirely rely on the Ledwall-Wolff target, which is less influenced by noise and thus more stable. This statement is false. Unlike some other methods, ShrunkCovariance does not automatically find the best ShrunkAGE value through cross-validation. You have to either choose the ShrunkAGE value yourself, or use another method, like Ledwall-Wolff's, to estimate it. This instruction tells you that more than one of the following statements could be correct. You need to carefully evaluate each statement about the "ShrunkCovariance" estimator to identify which are true. I see this as a super important point. ShrunkCovariance really shines when you have way more variables than observations. The usual covariance calculation can become unstable and might even produce a singular matrix, meaning it can't be inverted. ShrunkCovariance helps prevent that. This statement is false. ShrunkCovariance doesn't magically figure out the best shrinkage level on its own. You have to either supply the "shrinkage" parameter manually or use a separate method to estimate it. It's not automatic. The "shrinkage" parameter acts like a dial. At 0, you use the plain sample covariance. At 1, you completely switch to the Ledwall-Wolff estimate, a more stable version. Any value in between creates a blend of the two, finding a balance between using the data directly and using a more robust alternative. This is a big advantage. A positive semi-definite covariance matrix is mathematically well behaved. This ensures valid results in most statistical calculations. It avoids problems that could occur with a noisy or high-dimensional dataset using other covariance methods. This section introduces the core problem: evaluating true, false statements about the ShrunkCovariance estimator in Sklearn. We'll examine each statement's validity based on our understanding of covariance matrices and the ShrunkCovariance method. It's a quiz on your knowledge of ShrunkCovariance in Sklearn. I will guide you through it. Get ready. I find this statement to be true. The ShrunkAGE parameter acts like a dial. Setting it to 0 means I use only the sample covariance matrix, no fancy adjustments. A value of 1 means I completely replace the sample covariance with the Ledwall-Wolff target. The values between 0 and 1 create a mix, blending the sample covariance and Ledwall-Wolff target to balance accuracy and stability. The Ledwall-Wolff target is a more stable, less noisy estimate of the covariance matrix. I agree with this statement. ShrunkCovariance is awesome in high-dimensional scenarios, lots of features, few samples. In these cases, the sample covariance matrix can become unstable, perhaps even singular, non-invertible. ShrunkCovariance helps by regularizing the covariance matrix, making it more stable and less likely to be singular. This improves the reliability of further calculations. Imagine trying to solve a complex puzzle with many pieces but only a vague idea where to start. ShrunkCovariance is like a strategy to simplify that puzzle for easier solving. This statement is also true. One of the best features of ShrunkCovariance is that it always generates a positive semi-definite covariance matrix. This is important because a non-positive semi-definite matrix can cause problems in other calculations, similar to a badly balanced equation. ShrunkCovariance prevents this. I would disagree with this statement. ShrunkCovariance does not automatically do this. The ShrunkAGE parameter must be provided or estimated by some other method, such as using the Ledwall-Wolff method, which is frequently used in conjunction with ShrunkCovariance. It doesn't automatically use cross-validation to figure out the best ShrunkAGE value. Think of it like this: you must select the best tool for the job manually. This refers to a specific function within the Sklearn library in Python, used for calculating covariance matrices. Covariance matrices describe how different variables in a dataset change together. Scikit-learn's ShrunkCovariance is designed to improve the accuracy and stability of these calculations, especially when dealing with large datasets. It's like a supercharged version of a regular covariance calculator. This section introduces a multiple-choice quiz about the ShrunkCovariance function. You'll be asked to identify true statements about its capabilities and limitations. Get ready to test your knowledge. This sets up the multiple-choice questions focusing on the characteristics and correct usage of the ShrunkCovariance method. Each answer option will explore a different aspect of how this function works. The shrinkage parameter lets us adjust how much we trust the sample covariance, calculated directly from your data, versus the Ledwall-Wolff target, a more stable, theoretical estimate. A value of 0 means we completely trust the sample covariance. A value of 1 means we completely trust the Ledwall-Wolff target. Think of it as a slider controlling the balance between your data's direct calculation and a safer, smoothed-out version. ShrunkCovariance really shines when you have many more variables, features, than data points, samples. In such cases, the standard covariance calculation can become unreliable or even impossible to compute, singular. ShrunkCovariance overcomes this by adding stability and making calculations possible. It's a lifesaver for high-dimensional data. I want to emphasize that this statement is incorrect. ShrunkCovariance does not automatically find the best shrinkage value. You need to provide that value or use another method, such as Ledwall-Wolff's method, to estimate it. It's a bit like saying a car automatically chooses the best route without needing directions. That's not how it works. Although a diagram would be helpful, I'll just remind you that there's no diagram provided in this text to be described here. This section introduces the core problem: assessing the ShrunkCovariance method in Scikit-learn, a Python library for machine learning. We're evaluating its ability to handle financial time series data, which often has high dimensionality, many variables, and noise. The goal is to determine whether ShrunkCovariance provides a reliable estimate of the covariance matrix under these conditions. I'm checking whether ShrunkCovariance always produces a valid covariance matrix. A positive semi-definite matrix is a must in many statistical applications, and ShrunkCovariance ensures this. Even if my data is noisy or has many dimensions, this is a major benefit. Here, I'm looking at how much ShrunkCovariance relies on different inputs. The shrinkage parameter lets me adjust the mix between the sample covariance matrix, directly calculated from data, and the Ledwall-Wolff target, a more stable, theoretical estimate. A shrinkage of 0 means I fully trust my sample covariance. 1 means I completely trust the Ledwall-Wolff target. It's like a slider to control how much I trust my raw data versus a more stable alternative. This statement addresses the high dimensionality problem. I'm confirming that ShrunkCovariance excels when I have many more features than data points. In this scenario, the usual covariance calculation often fails. ShrunkCovariance helps to avoid such pitfalls by providing a stable result. I'm checking if ShrunkCovariance cleverly figures out the best shrinkage value by itself. It turns out it doesn't. I have to either set it manually or use an estimation method, like Ledois-Wolfe. This is important because a poorly chosen shrinkage can lead to inaccurate results. I'm assessing how well ShrunkCovariance, a scikit-learn tool, handles covariance matrix estimation, especially with noisy or high-dimensional financial data. I'll be focusing on its ability to produce a reliable covariance matrix. This question tests my understanding of ShrunkCovariance. I need to choose which statements accurately describe its properties and how it behaves. The ShrunkCovariance parameter is a key control. It mixes the sample covariance matrix with a more stable target, Ledois-Wolfe. A value of 0 means I use the raw sample covariance. 1 means I fully rely on the Ledois-Wolfe target. This helps me control the trade-off between accuracy and stability. A positive semi-definite covariance matrix is crucial. ShrunkCovariance ensures this, even when data is messy or high-dimensional, preventing issues in later calculations. That's a big plus. When I have many more variables than data points, the sample covariance becomes unreliable and may be singular. Non-invertible. ShrunkCovariance really shines here. It makes the estimation more robust. Unlike some methods, ShrunkCovariance doesn't do automatic cross-validation for selecting ShrunkAGE. I need to provide or estimate that parameter myself. This controls how much I shrink the sample covariance towards the Ledois-Wolfe target. 0 is no shrinkage, 1 is full shrinkage. This matrix shows the relationships between different variables in my data. ShrunkCovariance helps me get a better estimate of it, especially with challenging data. This is the specific scikit-learn tool I'm using. It's designed to produce a more stable and reliable covariance matrix. I'm working with financial data that changes over time. It's often noisy and high-dimensional. This makes standard covariance estimation techniques difficult.